Okay, thanks for having me. It's a really great event so far, so I hope to add another great talk there. Cool. So yeah, at Skymind we do deep learning for enterprise, and this talk is specifically tailored to explain to you kind of what we do, how we do it in a specific setting here. So the talk is called From Experimentation to Production, and this is kind of the important part. So I'm going to argue that oftentimes in data science teams in the real world, in companies out there, so you have data science teams that do a lot of experimentation, and then there's the production side to it, right? And you kind of need to bridge the gap there. So and we created Scala and Python APIs for our core product to exactly address this problem, okay? So that's too much. Okay. So the agenda is this. So I'm going to talk to you about Skymind itself and which products we have, and be a little bit more specific afterwards what experimentation versus production really means. Okay. All right. So it's amazing. I expect the same, right? Okay. So right. And then after having made the setup straight, I will introduce 4 products that we currently have that are Scala or Python wrappers to our products that we think are quite useful for data science teams in the real world. Okay. So to introduce us, Skymind is a small startup that has been founded in 2014, and we are globally distributed around the world. So we have 35 people, but actually sit all over the place. So this would be me here in Hamburg, Germany. And the orange dots are the important ones. So Chris Nicholson here is from San Francisco. We have our headquarters there as well. And CTO and co-founder Adam Gibson is in Tokyo currently. Okay, so we serve mainly enterprise customers, so big customers. We have 14 enterprises currently working with us right now. And what we do is essentially 3 things. So we have an open source platform, Deep Learning for J. I'm going to talk about this in a second. And we have an enterprise distribution for that. So you can buy that enterprise distribution for your enterprise and get so to speak enterprise support. Another thing we do is we provide training for our platform and for our products, and we also do proof of concepts, case studies, and help customers build their internal machine learning and deep learning pipelines. Okay. So it's a team of 35, mostly engineers, so it's very engineering heavy what we do, and we're really focused on the open source platform as well. So it's quite a popular framework all in all. So I would say actually it's one of the most popular Java open source projects out there right now. Cool. So the tools we have at Skymind are as follows. So this is just a little snapshot. We have a few more projects out there that might be interesting for you. But at its very core, we have 2 things, if you like. So it's Deep Learning for J and ND4J. ND4J is a very performant tensor library for the JVM. And I'd claim that it's pretty much the only competitive one out there. So we have really interesting tooling. It's very highly optimized for both GPUs and native, and you can swap your backends, activate CUDA, cuDNN, whatever. So if you're into that, you can have very fast tensor operations there. Deep Learning for J is built on top of ND4J. So it's a general purpose deep learning platform for the JVM. Yeah. So you can build, train, and deploy neural networks right there. So a few other tools that are pretty interesting and popular is, for instance, DataVac. DataVac is an ETL tool that you can use to prepare your data, which is then fed into the algorithms you're interested in, right? We also have Arbiter, which you might want to check out, which does hyperparameter optimization for those neural networks. And we also have a fairly new project that does reinforcement learning for Java. And, for instance, integrates with OpenAI Gym, so we have a Java client for that as well. Okay, right. So roughly put together, our deep learning stack, very simplified, looks like this. So data comes in, you use data back, which is here proposed as the Rosetta Stone of vectorization, so you do all your ETL processes in that way. And then you create a deep learning model using deep learning 4J, ND4J, and outcome predictions, classifications, whatever. Okay. So I already mentioned that we have GPU, CPU integration. But what's also interesting is we have a lot of popular integrations with other existing frameworks like Hadoop, Spark, and we're obviously Dockerized as well. So that would be that on a very high level. Okay. So if we take a step back, so I told you that D4J and ND4J are the kind of at the core of our open source stuff. What we built in the last few months, or maybe the last year, starting last year, is building more and more convenience features for data science teams out there. Okay. So on the side of ND4J, we have a new product called Jumpy, as you like. And it's really a Python interface to ND4J. So it's kind of a wrapper for ND4J arrays, and you can access it from Python. And so another thing is we have a Scala wrapper also for ND4J that looks and behaves like Numpy. So both of these are might be good solutions for you if, for instance, your company is on a Java stack, but you would like to do your good old Python stuff, but you just can't have it, right? So we have those two libraries that essentially equip you with all the tools that you already have, but it's under the hood. It's really ND4J, right? I'm going to talk about those 4 blocks here in the bottom in detail, right? So this is just the first overview. On a high level, so for deep learning 4J, we built something called model import. So there's a few high-level libraries out there, especially serving the Python ecosphere, that produce models in a quite convenient way that you might want to import into our ecosphere. Yeah? And so the model import currently includes Keras, which I hope some of you know, and also by association TensorFlow, Theano, CNTK, Caffe, and MXNet eventually. Okay, and the last part I'm going to talk about is Scarlet, which is high-level Scala API designed for deep learning 4J, specifically for data scientists to make access to deep learning 4J easy. Okay. Oops. Okay, so experimentation versus production. What does that mean? So usually when you start out, I'm going to assume that you're maybe the prototypical audience here is maybe a data scientist. Maybe you have worked in a company before, maybe you haven't. Yeah. So, but usually if you experiment with, and it doesn't really matter if it's deep learning or whatever modeling you do. So just a general experimentation setup for machine learning, and in this case maybe a supervised machine learning setup would be you have a loading phase for your data. So you get your raw input and you have to massage it somehow, do some ETL, prepare it for your model to be fed in. And what comes out is some pre-processed data. And depending on which model you're exactly using, you might have to do some feature engineering for it to really work with your model. So then most of you should know that with deep learning, you get around of most of the feature engineering, but it's not always the case. Sometimes you still have to be creative on, about how to prepare your data, at least, right? Next phase would be model training, and what comes out of it is a trained model that you can test new data against, and evaluate the validity and generalization of your model, right? And what you do is, those evaluation metrics would compare the actual outcome to what you predict. So this is kind of your experimentation pipeline, right? And you want to do this cycle as easy and flexible as possible, right? So what really will give you gains in prediction quality is the ability to iterate quickly over this process, right? So speaking about experimentation requirements, what you would generally nowadays want is an open source framework, and preferably Python, because like most of the data science ecosystem and universe is currently done in Python. I mean, there's other interesting things that people do. I mean, you also have R and many other things that are interesting, but more and more we see like a conversion towards Python out there. Yeah. So, and what's also important for you in experimentation terms is you need some sort of insightful evaluation and debugging. Maybe you want to have a little UI that tells you about the progress of the learning, and something that gives you an insight what might be wrong about your model. Maybe you did some mistake in data preparation, or you didn't normalize your inputs, whatever. So there can be many things that go wrong. And so what you want to ensure, and I said this before, is a fast experimentation cycle. So you do this often. Yeah, you cannot expect just to put a model there and then it works like a blast. So, okay. And two other things that might be interesting for you if you work with colleagues in a data science team is you need to reproduce your results, and you need to collaborate in some sort. Yeah. So these are, roughly speaking, I mean, I don't claim this is like comprehensive, yeah, but usually those parts exist in your experimentation pipeline, yeah. So now let's look at production. So on a high level, so I clustered a few things around your machine learning pipeline that you just can't ignore in production. So if you're working at a company, you are faced with many problems, and how we do that right now from a cultural perspective is we just have many different job descriptions and roles, right? So you say the data scientist does the thing in the middle, and then the data engineer is kind of responsible to bring it all to production. And that may or may not work well, but pretty much every company I've worked for before struggles with exactly this thing. So integrating their data science team and their products into the production system, yeah? And that's kind of a very different beast. And well, you might argue, for instance, that okay, I'm just doing the modeling. It's without a doubt for a data scientist the most interesting part. Yeah? So you could refrain and say, all right, we're using cloud services that just deliver our stuff like that. But as it so happens, at least for us at Skymind, many enterprise customers, big and large, I mean also startups face the same problem. They don't want to just put their data out there on some cloud-based systems, but they insist on having an on-premise solution. So most of the time, you have your production system already before you do the machine learning. So at least for all older companies and enterprises, it is like that. They already have their stack. And if you do something new, you have to integrate with that. So it's cool if you can do magic with your deep learning framework in Python, but if you can't manage to bring it to production, that's bad. Okay. Okay, and specifically, what you have to do to bring stuff to production is you have to cater for various data sources. So usually, at this age we're living in, it's like you get usually high velocity of data. It's highly heterogeneous. You get data from user sessions that are all over the place, and you have to aggregate them in a real-time system. So for most companies, so the good old times where you just had a relational database that through SQL or whatever a data scientist can program against kind of over, right? You have more complicated things like distributed systems and storage, okay? So you integrate various sources of data, and you need a proper ETL pipeline for that job. So that needs to be stable and reliable, can't afford any downtimes there. So you have also distributed storage, and also if you're in a real-time business, you also face the problem of streaming data. So like the experiment you do offline with your data might just not cut it, yeah? Because you get in tons of data every second or so, and at least you have to collect it for your next batch processing of your model. Right, so this kind of relates to real-time data preparation. And well, also again, depending on your company and your use case, you might need parallel training as well. So I don't know, think of online advertising or so on a huge platform for your online shop. Yeah, if you have tons of user data coming in every second, and you have a complex neural network that trains, I don't know, trains longer than 1 day, but you need to deploy a new model every day, then you're kind of screwed. Yeah? So you might run into trouble with stuff like this as well. So you might want to consider to parallelize training, and usually you can't do that with your tooling. Okay. Then at the very end, you have stuff like model serving. I mean, the model has to live somewhere, and with pretty low latency, give you answers. So again, if you think about something like Facebook Exchange, where you can buy advertisement places in real time, your prediction latency to decide whether to enter into buying this ad is like 100 milliseconds. So you have to be really smart about this. So especially if you have a model that has complicated ETL and input processing, right? You need to aggregate user data and read the cookie and have the browser session and whatnot, and the historical data of the user. You have to be super fast. So this is not something that's terribly easy. Yeah? So even if you have a great model, you need to bring it there. Okay. So there's many other things, but I just mentioned a few here. Okay. So an example of a production stack that we offer at Skymind is our product called Scylla, the Skymind intelligence layer. So Scylla is a package. It's our enterprise solution that not only offers all the libraries that I discussed at the beginning, but also integrations with many real-world systems out there. Okay. So we account for many data sources. We integrate with Kafka for streaming or Storm. We have distributed storage of all sorts. I already told you about the vectorization with DataVac. And you can also choose a distributed runtime with Spark, or we have also a standalone parallel distribution. Okay, and you have hardware acceleration, and can apply then your model and serve it into production however you like. So it's a fairly broad thing. So this is just, this is just one example, right? I think the slide I had beforehand shows you that maybe if you're lucky, this part in the middle is always the same, but solving the surrounding for each and every company, it's always different. So this is kind of the complicated part. So there's no one size fits all. Okay, so just as we discussed experimentation requirements, we also have production requirements, which more or less reflect what I already said. So you also want to have open source, but what you mean by open source is something else. Yeah. So it should integrate with your existing stack, and many of the enterprise companies we work with, if not all of them, build on the JVM. Okay. What you also need is to make it work at scale and as a complete solution is you need a cross-team solution from your DevOps guy who deploys your cluster to the data scientist who does the analysis against this data. Yeah? So it should be scalable, containerized, fast. So you have a lot of buzzwords here, but it's pretty important, yeah, if you have a business with a ton of data. So your predictions need to be highly available, and yeah, if possible, you want to have a general purpose framework that allows you to play around with many different classes of models as well. Okay. So I argued in the beginning that often we have this gap between data science and engineering, or experimentation and production. So I think there's roughly speaking maybe 3 categories that applies to. So purely technically, you have a discrepancy in programming languages. So often your production stack differs pretty much entirely from what your data science team does. But that applies in particular also to the ecosystem around it and the tooling you use. So oftentimes there's little to no overlap between data scientists and engineers, right? And that manifests itself in a cultural difference. Often those groups of people don't talk that much with each other, and that's too bad, because it leads to this third thing. I mean, what I mean by cognitive is not one person can know it all and contain it all and build a company on itself. So you need specialization. That is a given. That's true, but you should avoid to build silos where one team just does one thing and then says, all right, now you ship it to production. Right, so the engineers in your companies are not some soulless monkeys that are totally eager to re-implement your model in a different language, right? Okay, here are some possible solutions or prepared ways that might work for you. In order to move closer together, you could aim at providing tools that many groups of people, in this case data scientists, engineers, can easily pick up. So in the next part, I will talk about our tensor libraries and how to access them from Python and Scala, which might help you to integrate it with your stack. And the same also on a more high level applies to the deep learning library itself. Right? And another thing you can do is you empower your data scientist by simply shipping their models to production. And we have something called model import, where you just build your model wherever you want, so to speak, and then import it into the deep learning 4J stack, and can further process it if you like. Okay. Again, I talked about ND4J already a little, but so it's a very versatile tensor library, and in fact it's pretty much the only option you have if you want to do n-dimensional things on the JVM. Yeah? So there's a few matrix libraries out there, but if you really want to do n-dimensional arrays, tensors, it's kind of the choice you have here. It's heavily optimized for hardware acceleration as well. And roughly speaking, I mean, it's not always the case. It differs from what you actually do, but it's roughly twice as fast as Numpy, which is cool. So something new we built, I will pick this up a second again. We have a new module called SameDiff, which is an auto-differentiation module. And auto-differentiation is something that is super important for deep learning. And libraries like Theano and TensorFlow have it as well, right? So if you build a deep learning model, you just specify the forward pass and the gradients that are necessary to propagate back your error terms in your model are computed on its own. Yeah? So we will have that soonish. So it's in early stages. All right. So we have those two wrappers that I mentioned initially. Coming to ND4S versus Numpy. So ND4S is n-dimensional arrays for Scala, right? I'm not going to show you any Java code here. So I'm just picking up the Scala and the Python stuff, right? So I act as if the other things don't exist. So if you want to get started with ND4S, essentially you just clone this repository, I mean, for a local setup, yeah? And use SBT, simple build tool, to publish it locally, and then you can just start a console, like an interactive console that you might know from Python, like IPython. It works pretty much the same way. So you just start that, and then you can, on the left, you see, you can create an array by specifying a range and giving it a shape. So it's a 3x3 matrix with numbers from 1 to 9, right? And then you can do all sorts of stuff with it. So you can add them, you can multiply those arrays, you can do a dot product with it, okay? And as you might see, so here on the right side is the Numpy comparison for you. Most of the stuff you see there is at least very similar. I mean, you can always look up. We have some cheat sheet that might help you in the beginning, but it becomes fairly natural to work with ND4S in this way. And actually, I do this quite often because this interactivity is really key. So it allows you to play pretty quickly with tensors on the JVM. So it's kind of cool. And yeah, so I did this one-to-one correspondence for you to see that they are structurally alike. And in terms of coverage, I mean, most of the operations we support. I couldn't put my hand on it's every single one, but most of the relevant stuff we do. Okay. And then also, I'm not sure how many of you write Scala, but you can do pretty awesome things with operators. So instead of writing np dot of an array with an array, you can do this almost humanly readable array dot array. So it is very very readable output that you get from this. Okay. So this time let's turn to Jumpy. Or Jumpy. I'm always unsure how to pronounce this because I think people say Numpy, but in order for this pun to work, you need to see Jumpy, right? So it's, I don't know. Cool. So Jumpy is really a different animal, if you like. So whereas ND4S is simply a Scala wrapper for ND4J, Jumpy really brings ND4J and our tensors to Python, right? So you can write in Python, but what it really does is under the hood, you operate with Java tensors. But it looks as if you do Python. So that's pretty cool. And it interoperates with Numpy. So what you see here, we import Jumpy and Numpy and a few operations from Jumpy. And how you start this whole process is you init your Jumpy session, right? And what you do next is you start with a simple Numpy array. So it's this space here. And what you have here as convenience wrapper is you call from NP, from Numpy on this array. And what comes out of this, called ND4JR here, is really, it will create under the hood an ND4J array that uses the same memory address as the original Numpy array. So there's no network overhead or something. So we directly point to the same thing. Okay? But under the hood, yeah.
Are you using something like CFFI?
So the wrapper behind this that powers that is called Genius. Yeah, so you might want to look this up. Yeah. Okay, and from this point on, you can essentially do the same things as we did before, right? So you just have something that lives on the JVM, but it acts and feels exactly the same as Numpy, if you like. And well, the latter part doesn't have to interest you right away, but if you're familiar with auto differentiation, this is how you would create a variable that you could then differentiate for deep learning, say. Okay. So we discussed the first two low-level wrappers, the Scala and the Python wrapper for our tensor library. Now let's move on to the higher level stuff, right? So deep learning for J is also, as mentioned before, a general purpose deep learning library. Many of the models we've heard about before, like bidirectional LSTMs or convolutional neural networks, feed-forward neural networks, you find in deep learning for J already. you can do parallel training and also parallel inference. And we have kind of specialized code and use cases where, well, you might want to use, you have to use essentially GPUs for parallel training, but often at inference time for prediction, the CPUs are faster, right? So and we kind of do this automatically. So under the hood, it's powered by ND4J, and we have some cool features like Keras model import and a Scylla wrapper that I'm going to show next. Okay, so model import. So there's a popular high-level deep learning library called Keras that I've been working with since I think 2014 in its early stages. And the cool thing about Keras and how it represents itself today is that it comes with many backends. So I don't know what you use specifically to do deep learning, but Keras defines itself as an API spec for deep learning. So it's kind of the front end to deep learning, and many more people try to integrate with it. Yeah? So at the beginning, a few years back, it was only Theano. Then shortly after came TensorFlow, and by now CNTK also integrates with it. And if I'm not mistaken, MXNet also has a preliminary integration into Keras. So you can essentially choose your backend, but on the front end it always looks the same. Yeah. So and what makes Keras powerful is that it has this very elegant and intuitive feel to it, so people get started with it really quickly. It might be like the number one reason why people pick it up, because it's so easy to understand. So the API is cool, so and people like it for it. But then again, so Keras, for instance, has always claimed that it's for fast experimentation. It's a research framework, if you like. So well, if you do stuff like TensorFlow in the back, you have some more utility function. That's for granted, but just from coming from there, you don't have any of the convenience features that we would like to see in production, what I discussed earlier, right? So what we do is a model import into DL4J. So there's a serialization format in Keras that allows you to export models, and you can re-import that into DL4J. And once you have that, you have our full stack at your disposal and all the integrations that we're having, right? So you can do your experimentation as you're used to, but then ship your model to production this way. For instance, what you could do is you start out with, well, some sort of model. You do your first shot, or you have a pretty decent model already. You store this with all the weights, with all the training configuration, etc. And you pick it up again in DL4J. And what you could do is just use it there for prediction, or you could further use that for further learning, right? If you're okay with the model, you just pick it up there, and you can retrain it, or you can do transfer learning, or whatever. So it's pretty flexible in that regard. Okay, let's just look briefly at a use case, just for explaining how we would do that and how we structure a Keras model, yeah, and import it. So think of a very simple use case that many companies have. So I think it's a pretty prototypical thing. Yeah? If you have some sort of online shop, you often want to recommend the products you're having in your shop, right? So this matrix I'm suggesting here, products by users, would list maybe the user IDs you're having and the product IDs you're having in your online shop. And well, the items in this matrix would be, if your user bought that item and gave it a 5-star rating, then you have a 5 there, right? So it's a big matrix that you want to infer stuff from. So maybe you have new products, you want to recommend new products, or you have new users, which old products do you want to recommend? Okay, stuff like that. And classically, what you could do is you look at your data and you extract features from users and products on your own, right? So you could, for instance, say, this user, I know his age range, or I know which gender he has. So I can extract features from that on my own. And I can do the same thing for my products, right? So if you have a washing machine, you know, maybe its price range and so on, okay? So you can absolutely do this, and like one of the ways to classically do that would be matrix factorization. So there's a lot of techniques about that, and I'm not going to explain in more detail what this really does. So high level, what you do is you want to recommend new stuff, and the input features are, well, doesn't even have to be that, but you can one-hot encode your user IDs and products. So like for user ID 322, you have a vector with all zeros and the one at 322nd place, right? And the labels are the normalized ratings, right? So if you have a 5-star rating system or something, then you would predict something between 0 and 1. But you could also apply this in a different range just to did the user buy or not. That would suffice as well, right? So would practically be the same thing. And I mean, this particular setup is pretty ubiquitous. You find this everywhere. Like the Netflix prize that has been issued a few years back is pretty much exactly that. Yeah? Okay, how could we model this? So I don't really assume that you know any Keras, but I will explain you how you can do that with the deep learning. So I mentioned that you can specifically create features for your users and products, but you don't have to. You can learn them automatically with deep learning, as is always often the case. So what we can do is we can take the users and products and embed them. So there's something called an embedding layer that takes a numerical input and produces a vector of a fixed length from it. Yeah? And this vector of fixed length is exactly what we want. It's a feature. We just don't know. We cannot pinpoint what the meaning of that feature is. But usually we don't care, right? So what we do is we compute an embedding for our users and we compute an embedding for our products. And those are two vectors we can concatenate. So, and well, then we just have a large vector. And what we can do is just chain a deep neural network onto that. So it's just a vector, and we have predictions, right? We have the star ratings. So you choose whatever architecture you like. You've seen feed-forward networks in most of the talks, I guess. So I'm not going to explain that in detail, but essentially it's a way then to produce predictions for your vector for this given output. Okay? So now the way to do this in Keras, quite simply put, is you start with two sequential models. So you initialize them. So you have one model for your users and you have one for your product. And in each you create, you add an embedding layer simply by saying model add, right? So that's kind of the interface that Keras provides, at least in the sequential case. Yeah? So you start with something, and then you just add layers sequentially, if you like. So if you can't really make any sense of that, the important thing is that you have a kind of a direct one-to-one correspondence between the left and the right. So I mean, if you know Keras, you know it translates to this picture. If you know the picture and understood what I just said, you can almost write the Keras code if you spend like an hour with the API. Yeah. So you have to, I mean, continuing with this, we embed our products and our users with vectors of length 128, and then we chain. I think in this case I chose 4 dense layers to produce one output. Yeah. So to wrap this up, so you start with the sequential model, you merge those two embeddings, and at the very end you compile your model with a given loss with an optimizer. So in this case it's just mean squared error and stochastic gradient descent, right? And afterwards you're kind of already done. You can fit your model and you can predict against it. Okay, so it's very just a few steps. So from your architecture and your first idea to a given model, it's usually a pretty quick pass. Okay. So how do we do a model import then? If you have your given model, what you can do is you can just say model save, and this produces some HDF5 file. So it's a very efficient data format that you can store all the weights and the architecture and everything. And so what you can do then, and this is the only Java snippet, you can pick this up by simply specifying the file, this model h5 file. And the key abstraction, or one of the key abstractions in deep learning for J, is the multi-layer network. And you can recover the Keras model in DL4J, so it gets compiled in a deep learning for J model by simply saying Keras model import sequential model, right? And you provide the model file, and you specify if you want to further do training or not. And that's pretty much it. So then you get your data from somewhere, yeah, and then you can do predictions on your model. So that can be very helpful, and we have done this in a lot of places already. So for instance, we had quite a few use cases recently where we didn't quite have like 1 or 2 layers supported in deep learning for J, or let's say not layers, but maybe something like a loss function or maybe an optimizer that we still don't have, yeah. But it was available in Keras, so you can train the model there and import it in deep learning for J. And since you might not need any further training, the model itself, as a trained model, still is at your disposal, and you don't have to worry about this. Yeah. Okay, cool. So the last thing I'm going to talk about is Scarlet. And Scarlet is an intuitive high-level API for deep learning for J, and it's modeled after Keras. So it pretty much looks like Keras. So we did this on purpose. And those models obviously just compile into regular deep learning for J. So it's just a matter of specifying those models. But under the hood, it's just deep learning for J, right? And we chose Scala as, it's a strange slogan, but we think it's kind of Python for production. So I mean, many people are sometimes scared by the sheer amount of stuff you have in Scala. But if you restrict to the right context and use the right language features, you can idiomatically write it very similarly to Python. And it can help people to pick it up quite quickly. So we try to do that with Scarlet, right? So I will not discuss this here in detail, but essentially on the right-hand side, you have a Keras model again, which does exactly the same thing as we did before. It's actually a convolutional neural network, and what you do is you chain 2 convolutional networks, followed by a pooling layer. You flatten the output, you add some dense layers, you get your prediction. That's it, okay? And I hope you appreciate that structurally, on the left, what we see is Scala code. And maybe apart from the first line where you have a val in the top corner, you might not even notice that this is Scala, okay? And so we have kind of this look and feel that allows for fast prototyping with deep learning for J without you noticing, so to speak. Yeah. So and it's not that our Java interface is awful or anything. It's quite easy to pick up as well. But if you have your average data scientist who is new to the business, it might help him a lot actually to pick up such an interface as compared to maybe more boilerplate heavy Java stuff. Yeah. So Outlook. What we want to do next, we can't really tell when, but we want to apply this auto differentiation tool, samediff. 5? Aha, amazing. We want to apply this on top of JumPy, the Python interface, to create a backend for Keras, right? So just on top of the other things I listed, so you could then also use deep learning for J as a backend. So You need to install the respective Java libraries, of course, because it translates into Java arrays under the hood, as I explained. But that's cool, especially given the speed of ND4J, right? So this might be attractive. And what we're also actively working on is feature parity with Keras. So we have like 90% of it, but we need to work further on it to have full model support right now. And also Scarlet, if you're interested in it. So we have a lot of low-hanging fruit still. It's pretty alpha. If you want to help us develop this, would be cool. So we want to make this a first-class member of the deep learning 4J ecosphere and continue work on this. Yeah? Cool. All right. If you want to learn more about what we do in general, so we have a few things coming up. It's a bit of shameless self-promotion as well, I'm sorry, but on the left you have a book by our head of field engineering and our CTO about deep learning for Java. So this book, this O'Reilly book, Deep Learning Practitioner's Guide, is really about deep learning for J. Then the middle one, which was published last month, is actually a book written in Scala. So it does machine learning with Spark, if you're interested in that. And on the right, you might appreciate my artwork, but this will hit early access in November, I think. So together with a colleague from San Francisco, we're writing a book. It's more like an homage to DeepMind's work on AlphaGo. So it's about deep learning in the game of Go. That might be an interesting use case. And this one is written in Python. You might like this as well. So, and if you're a Go player, please grab me. I'm pretty much into it and on all the servers. Yeah, cool. All right, key takeaways maybe. So take production seriously, right? I mean, you might want to handle your interesting use cases and just work on the models, but it has to integrate into everything else around you, right? And work on ways to work together with the surrounding teams. Yeah, don't build silos. So you might want to consider one of our wrappers, maybe Scala or Python, to bridge exactly that gap. And maybe as a last point, I think you can kind of have both worlds. I mean, we have different requirements in experimentation production, but if you do it right, especially if you think about something like model import, it might just work out well that you import your work without any friction. Okay? So thank you very much for your attention.